Dear participant, welcome to 6 days online FDP on the future of quantum computing and high performance computing. Today, day 2, session 3. Today with us, Dr. G. Fatima, Professor and Head of the Department, CSE, Adiyaman College of Engineering. So it's my pleasure to welcome Dr. G. Fatima, Professor and Head of the Department of Computer Science at Adiyaman College of Engineering, Hosur, Tamil Nadu. With over 27 years of teaching experience and 17 years in administration, Dr. Fatima has been guiding force, mentoring team at the Smart India Hackathons. She has published 33 research papers, presented 29 papers at conference. Additionally, she has authored 11 books and book chapters and received research grants from UGC, AICTE, and other esteemed organizations. Dr. Fatima has been honored with several prestigious awards, including the International Educators of the Year 2022 Award and the Faculty Excellent Award from Infosys. On behalf of everyone here, I warmly welcome you, ma'am. And we are eagerly looking forward to your insightful session today on quantum search algorithms, Grover's explained. Over to you, ma'am.
Thank you, Vinod, for the wonderful start.
Thank you, ma'am.
Shall I start the session?
Ma'am.
Okay. So
you can share your screen.
Okay.
Yes, ma'am, visible. In full screen.
Okay.
Yes.
I hope my screen is visible.
Yes, ma'am, it is visible.
Clearly.
You may proceed.
Okay. A very good evening to one and all present here. First of all, before getting into the session, I'm very happy to welcome you all for my today's session on quantum computing, and specifically the given topic for me is Grover's algorithm. And I'm very happy to connect with you all in this AICTE sponsored ATAL FDP on future of quantum computing and high performance computing. So before getting into the session, I would like to thank Dr. P. Selvam sir, who is the chairman of PSV Group of Institutions, and Dr. Vivek, the secretary of PSV Group of Institutions, Dr. P. Lawrence, principal of PSV College of Technology, Dr. M. Srinivasan, professor and head of IT, who is the ATAL coordinator, Dr. S. Chandrasekhan, professor and head of CSE, who is the ATAL co-coordinator. And also, as well as I thank AICTE and for giving me this wonderful opportunity of sharing my knowledge with you all in the today's evening. I hope I am audible.
Yes, ma'am, audible.
Okay. So it is really a great pleasure to join you all in this session. And as I was telling that, I have been assigned the topic of Grover's algorithm, and really excited to share whatever the knowledge I have with you all. I do not know how much of you all are already working on this quantum computing. May I know any people those who are already working on quantum computing? How many participants are there? How many of you are working with the quantum computing? Just to get an idea about the audience.
You can only speak now.
Okay, okay. So having come to the second day of ATAL's FDP, before getting into the Grover's algorithm, even I have slightly attended the yesterday's session also. So I want to give some introduction about the quantum computing, which is very much essential to get to know about this Grover's algorithm. So before we delve into the quantum computing, let me take a moment for giving the introduction about the quantum computing, and then I'll carry on to the Grover's algorithm. Okay. Okay. So this is the agenda of my today's presentation. I'll be giving the introduction to quantum computing, and then it is followed by the qubits and the quantum gates. Then we will move on to the Grover's algorithm. Then I will share just why we have to again concentrate or focus our view on towards the quantum algorithms. Just giving you an idea on quantum app development, quantum computing applications, and what are the challenges we have with this quantum computing. So let me start with the again everybody may aware of this Moore's law, which states that number of transistors on a microchip doubles approximately every 2 years, and this is again a statistics which gives you again the number of transistors again in the microchip starting from the year 1992 to 1972 to 2020. Again, this actually, the Moore's law has driven the exponential growth of the computing power, and actually it has led to the remarkable technological advancements, which is what we are experiencing today. But again, this has worked for a long time. But what is the problem? What we are facing now today is actually we have reached the physical limits of miniaturizing the transistors, because you can see that number of again when we just having more and more number of chips, then it has the transistors have become so small. Again, it is like to the almost similar to the size of the atom. As a result, it has become very difficult for the to make the computers faster using the classical computing architectures, and it has become very challenging too because of the heat dissipations and the effect of it. So though it is not the scope of my presentation, just given you a glance of what is the Intel says again about what is the work that has been carried over by the Intels. And here you can see that actually the Intel it firmly believes that Moore's law has not come to an end because of its own innovation. And with the ongoing breakthroughs like process, packaging, and architecture, and the Intel is finding new ways to double the number of transistors per device so that it can meet the growing customer demands. So actually, Intel is very steady in its goal of achieving approximately 1 trillion transistors on a single device by 2030. This is actually an ambitious target which gives its commitment to advancing technology and redefining the possibilities and driving the industry forward. Uh, this is the state of the Intel. But we can get into the another perspective that we are as we are approaching the physical limits of the miniaturizing the transistors. Further shrinking them has become a significant challenge, though some industries are working towards it. And at this juncture, now the quantum computing has come into picture. Unlike the classical computer, the quantum computer rely on the binary, like it doesn't rely on the binary transistors. It leverage actually the principles of quantum mechanisms to perform the computations. Actually, it relies on the principles of quantum physics such as superposition, entanglement, which is giving it to process the information in a complete different way. So let me start with what is a quantum computer. A quantum computer is a machine that performs calculations based on the laws of quantum mechanisms, which is the behavior of the particles of at the subatomic level. And then what is quantum computation? It is we all know about what is computation. So computation is coming to the quantum computation. It depends on the operands and the operators, and this follows the laws of quantum mechanism. So a quantum computer, if you see that, it looks very different from that of the laptops or the desktop which we are using it. And this picture shows you how the quantum computer looks like. See, it is like entirely different what we are having as other classical computers now. I can observe that. I think I am able to see my mouse movement. You can observe that it looks like a refrigerator-like structure. It actually, though not only looking like a structure, again, actually, this quantum computer, it operates in extremely cold temperatures, which is often close to absolute zero. This is done to maintain the dedicated quantum states. So the main components typically housed inside is a cryostat, which is a cylindrical box. See here, which has been mentioned as A. This is it is like a cooling system resembling a refrigerator or a large chandelier. And inside the chandelier or the cryostat, you can see a complex structure with the golden shiny wires and plates hanging down, which is called as the quantum chandelier. And though it is not visible here, let me just get into here. You can see here. So you can see this, and you can this is a complex structure with the golden shiny wires and plates hanging down, and this is called as the quantum chandelier. And you can see that inside this cryostat, you can see such structure. And you can see that the wires carry signals to and from the quantum bits. And if you see that the actual quantum process where the qubits are located is very small, typically a chip-like structure at the bottom of the chandelier. And if you see that these qubits, they are made from the superconducting circuits or trapped ions depending on the technology. You can see hundreds of wires. Here you can see that hundreds of wires and cables connect the quantum chip to control and the measurement systems. And these are needed to send the signals to the qubits as well as to read their states. And you can see here the shielding which is used to protect the qubits from the noise and the interference. And here whatever has been mentioned, that is A and D is nothing but the cylinders or the cryostat where the quantum processors and the cooling system is placed. And the B and C, they are the support systems for what inside, which is inside the cylinder, like a power supplies, cooling glass, and then control box, and this is and the entire thing has been shown here as a shielded structure in the D. I hope it is clear. Next, we will move on to the qubits, because this is the star. You can say that star of the quantum computer is nothing. Superstar, you can say the superstar of the quantum computer is nothing but the qubits. And now coming to this qubits, quantum computers use quantum bits, which is called as the qubits. And the qubits are very special because they can be in a state either 0, 1 or both 1 and 0 and 1 at the same time. If you come across the traditional our classical computers, so you can just imagine it is a single bit can be thought of as a piece of a binary information, and it can be represented as either 0 or 1. And they are represented as either an electrical voltage or the current pulse. But if you come across this qubits, it can this which is entirely different from that of the classical binary bit. So it will be in a three different states, like either 0 or 1 or both and 1, 0 and 1 at the same time. And this both having 0 and 1 at the same time is called, this state is called as the superposition. But the general one, 0 and 1, are referred as the basic state. And we can label the states as you can see that this notation, I will be giving you this about this notation in the next slide. And actually it is pronounced as, we can use this pronouncement as Kate 0 and Kate 1, and this is notation is called as the Dirac notation. Now let me give you the insights on the key features of the qubits. The first feature is the superposition. As I told you, the classical build can be in a 0 or 1, but the qubit can exist in the combination of both of the states at the same time. And now the superposition again of the state means the quantum system is in two states at a time until it is observed. And this superposition feature is very useful in the quantum computing. This is explained by this property of or characteristic of superposition can be explained through this diagram or picture. You can see that if you are placing a cat, and as well as the one which is something which is which could kill the cat, and this box is sealed, we cannot know if the cat was alive or not until we open this box. So it can be either in the alive state, or it can be in the dead state, or it can be in the superimposed state. So, but that That is, it can be in three different states, and until you break down the box or open the box, you will not be able to know what is the state. And this particular feature or this example can be analogous again, can be used to explain the superposition. Similarly, a very simple example of tossing the coin also you can have as an example for the superposition. So when you're tossing the coin, again when it is again for fall down again, like you can say that either it can be it can be facing the head or facing the tail. But when once you are flipping it, you may not know again it's coming and the coin which has flipping from top to bottom. It may be in either in the head state or in the tail state. So that state again having both the state at a time is called as the superposition. Again, next the feature is the entanglement. Here, the qubits can be entangled. That is, the state of one qubit is linked to the state of the another, no matter how much far apart. So, changing the state of one entangled qubit will instantly affect the partner, that is the one which is connected. Again, this property actually enables the powerful correlations and faster computations in the quantum systems. That's why this is considered to be a very important feature of the qubits. Okay, you can just have an example like if we say we have the two particles which are closely linked, and one particle is at my home and the other one is at your home. So whenever the behavior of one particle at my home changes, and the automatically it will affect the state of the other particle which is in your home or vice versa. So that is called as the entanglement property. The next one is the quantum interference. So quantum computers use interference to manipulate the probabilities of qubit states. So by amplifying the probabilities of correct solutions and cancelling out the incorrect ones, quantum computers can solve certain problems more efficiently, and which you will be observing that used in the Grover's algorithm too. So this superposition and the quantum interference are used, these characteristics are used in the Grover's algorithm. That's why I want to give insight on this key features of the qubits. Now let me move on to the notation, how it can the qubit is represented, the state of this qubit is. So you can see here the notation. I think you are able to watch where I am moving. So this notation is pronounced as psi. That is, if I am breaking down it further, so this vertical bar is pronounced as ket, and the Greek letter, this Greek letter is pronounced as psi. Okay, and then the angle bracket is also pronounced as ket. And so, putting together, the entire symbol is read as, though actually this is also ket, then psi ket. So instead of reading it twice, the entire symbol is pronounced as ket psi. Okay, and this is called as the Dirac notation or bracket notation. So, and so the quantum state is can be written as it is if you see this quantum state for ket 0, this is the quantum state ket 0, and it is represented as the vector 1 0, and ket 1 is represented as 0 1. And if you see this quantum state that is ket psi, it is expressed as alpha ket 0 plus beta ket 1, and this basis state is 0 and 1, and the superposition is again when you have a combination of both these states, which is alpha ket 0 plus beta ket 1. Okay, and where this alpha and beta are referred as the probability amplitude. And you can so once you can see here So here this alpha square and the beta square are the probabilities of measuring the qubits as either 0 or 1. So if you have more probability towards this 0, then it is in the 0 state. If you are having more probability towards the ket 1, then it is in the 1 state. And here this alpha and beta are nothing but the complex numbers. And I hope you are getting this notation because it is very important to understand the quantum again algorithms, again the quantum mechanisms, all those things. You are supposed to have this basic understanding of qubits as well as the qubit states. Again, next we will move on to how again there is other representation called as the block sphere representation. And this block sphere helps to visualize the superposition and the phase of a bit, which is very critical for this quantum computing. And this is a visual representation of a block sphere where the qubit state is represented. Again, the qubit state is represented as a point on the surface of this sphere. And the north and the south pole represent the classical states, that is ket 0 and ket 1. While any point on the surface is represent the superposition. And this actually, the block sphere provides a two geometrical way to understand the quantum states, that is pure state and the mixed state. See here, you can see that the pure state is represented on the points on the surface of the sphere, like ket 0, then ket 1, then plus ket plus and ket minus. All these are the again I will show you the other diagram which you will make you yeah, here it is not mentioned. Okay, so here so this is like a ket again whatever you have in the south pole, it is ket 0, and you can have whatever you have in the again north pole. It is here this is sorry, z axis, and then here the like you have it as the ket 1 is in the again minus z. Okay, and similarly you have x and the y axis, and the mixed states is the points inside the sphere which is not on the surface, and this is corresponding to the probability mixture of the pure states. And we can see here and the representation, the state is represented as because it is again once you have a sphere, you make use of again you have the angle again theta as well as psi and phi. Again here the state is represented as earlier we had represented as 0 and 1. Now here you can see that in this psi is represented as cos theta by 2 ket 0 plus e power I phi sine theta by 2 ket 1. Again now next we will move on to the vector representation. Again here you can see that all as I have given the ket 0 is represented as a column vector as 1 and 0, whereas ket 1 is represented in the column vector as 0 and 1. So here you can just assume that or you can easily remember that if it gets 0, then the first one again 1 is we have that is 1, it represents here 0, and the one here the second bit represents as 1. So since you are giving as since we are representing ket 0, it is 1 and this is 0. And if you come across this ket 1, 0 is again 0 is here it represents 0, so you are given as 0. The other entity represents 1, so you are representing as 1 over here. So this is how the ket 0 and ket 1 are represented in column vectors as 1 and 0. The other way again of representing the ket 0 is either you can go for the instead of column vector row vector also. So it is 1 0 here, or ket 0 1. Okay. And any arbitrary state, it can be represented as a ket psi, which is it is arbitrary state. So it is alpha beta represented as column, or you can have as alpha ket 0 plus beta ket 1. Okay, and here are the some of the examples of a valid quantum state vectors representing the qubits, and we are aware, as I told you now, we are aware this is ket 0 and this is ket 1. Okay, I think I can use. Is it okay if I'm using this ball pen if you're not disturbing? Okay. Okay. Yeah, I think this is ket 0. This is sorry, this is ket 0. The other one is ket 1, and these are nothing but the superposition states. Okay, so these are nothing but okay. These are the several valid quantum states, and you can. I told you that they are complex numbers. So again, I will show you the next diagram where you can represent it. Again, where this actual quantum states lie. Okay, and this plus and the minus are called as the ket plus and ket minus are called as the Hadamard's basis, and these are orthogonal to each other. And you can see here how this ket plus is represented as 1 by root 2 of ket 0 plus ket 1, and minus ket minus is represented as 1 by root 2 of ket 0 minus ket 1. So here, so you can observe that it implies that both the state 0 and the 1, they are they have the equal probability. Okay, that's how this state is called as the superposition state. Again, there is other one called as the, again you can see here, that is here it is ket I state. Again, that is represented as 1 by root 2 of ket 0 plus I ket 1, and minus I is represented as 1 by root 2 of ket 0 minus I ket 1. And I will show you that. See here. So you can see here, this is the ket 1 state. Okay. And here, this is ket 0 state. Okay. And then you can see here, this is the superposition state. Again, here, orthogonal it is, you can see that it is the other state minus. Okay, so if you are just considering this x-axis, again the y-axis, and then the z-axis, like that, you can just imagine again, and then you can see that all the different states, again each you can have as one is again 0 1, again then similarly you can see over here the other states also. And this is called as the spin quantum bits. It is represented in the spin form. Okay. So as I told you again, regarding this quantum bits, whatever we have saw is 1 bit. That is, we are just using this ket 0. So only 1 bit. And it takes this form of vector as 1 0, and whereas 0 ket 1 is taken the vector 0 1, and the state is represented using the psi notation of 0 ket. This is actually again the probability, as I was telling, this is alpha. Again, this is a probability of a get 0 and the probability amplitude of a get 1. So here, since it is one state, you can see this probability is 0, and here you can see this, the probability is 1. This is how a get 1 state is represented. Again, the square of these probabilities again indicates the probability of the spinning, which is as 1. Okay. And both this alpha and beta are complex numbers. That is very important thing which you are supposed to know. Now, here I have shown you that the quantum bits, whatever that has been referred or represented here is 2 bits. Now, here it is nothing but you have a that is 0. Again, it is a tensor product with the 0. Now, it is similar to this or that of the matrix multiplication, by which you can get this particular of how you represent get 0 0 as a column vector as 1 0 0 0. Similarly, 0 1. So 0 is represented as 0 1 0 and 1 is represented as 0 1. And if you take the tensor product of it, you get the column vector which represents the get 2 bits 0 1. Okay, so now you might have understood again about the notation let's get as well as tensor product and then matrix form of the representation. All these things you would have got it. Believing that here you can see here psi is nothing but alpha, beta, and then gamma and delta. Okay, so because you have if you have 2 bits, there are 4 possible states. Okay, that is similar to that of the once you have understood the binary concept. Again, you can easily and then you can easily say that if you have 2 bits, then possible number of states is 4 states. Okay, and these 4 states again it is given by the amplitudes, that is alpha, beta, gamma, and delta are the amplitudes for each of the qubits existing in the states. Okay, alpha is for qubit existing as 0 and beta is for the existing as 0 1, and gamma is for the existing qubits existing as 1 0, and delta is existing as 1 1. Okay, and here also you have to remember this putting all the squares of all the for all the amplitudes sum will be equal to 1. Now, having understood the qubits with the two quantum bits with the size of 2, now here I have given you an quantum bits of size of 3, and you can easily say that if it is 3 bits, the number of quantum states will be 0 to 7, right? Are you all with me?
Yes, ma'am. Yes.
Okay, okay. So now you can see here this 0 0 0. Again, I'll just tell you this 0 is again here represented as 1 0. Tensor product of again the next bit. You can see this. This is the next bit again 1 0. The next bit again 1 0. Okay. Now the tensor product of all these things, if you multiply and see, you will itself will come to know that this is how the column vector again you get it for the state 0 0 0. Okay. So similarly, if this again this whatever the slide shows is the column vectors of all the states. Now, if you are having this as a matrix, you can see that no, I'm not given here. So if you see this, now I'm giving you this all again. I can see this all the 7 bits. Okay. So if I'm considering all those things, you can see that all the diagonals will be 1. Okay. Consisting of this matrix. just having it as a matrix of all the states. So the first state, if you see that, again, I'm not having all the bits. So the first state, again here 1, then 0, 0, 0, and then second state, you can see here, that is 0, 0, 1 state. Like this, you can see that. Again, all the diagonals will be the diagonals. If you're having it as the entire matrix of all the states, then you can see like that. Okay. And then the next, I will give you difference between the classical and the quantum bits. So as I was telling you, I thought that I can ask you the questions, because having said about the quantum bits, I can ask you what is the difference between the classical bits and the quantum bits. Now, as I was informed that nobody will be allowed to again, everybody is muted, so I'll just monotonously, I have to say that this again the classical bits. Again, the difference is it can be in two states, that is either 0 and 1, whereas the quantum bits in the states either that is get 0, get 1, or it can a combination of the two states. And this classical bits can be measured completely, whereas the quantum bits can be measured partially with the given probability, because everything lies with the amplitude of that particular bit. Okay, and then classical bits are not changed by the measurement, whereas quantum bits are changed by the measurement. Once you start measuring it, because it may be existing in the superposition state, when you measure it, it can be in only in one of the state, just like a binary system. Okay, and that is either it can be in zero state or in the one state. As I was telling you, when you are flipping the coin, when it is falling down, when you are measuring it, then you can observe either it is in head or either it has a tail. But it can be in other states also, that is another, it is called as the superposition state. And that is when, but the important property or law of quantum mechanism is once you start measuring at the state, the state will get collapsed to one state. So that is the important law of a quantum mechanism. And that's how here, that is what mentioned, and that is the difference you have with the quantum bits. And the classical bits can be copied, whereas the quantum bits cannot be copied. Similarly, classical bits can be erased, whereas quantum bits cannot be erased. Now, having got the knowledge on qubits, and what is the advantage of using this qubits? Why we are talking about this qubits? Why, how it is again more special compared to that of the classical bits? So here, adding qubits, actually it increases the storage exponentially. But if you see that quantum power of the quantum computer, it doubles the power. Quantum with that is the qubit will double the power with every added qubit. So that's what I can put it this way. See, if you see this, it is, for example, if you want to double the power of a digital computer, which is with the 32 bits, then you have to have a double the bits. That is, you want to convert it into 64 bits. Only then the power of the digital computer gets double. Whereas, if you see the power of the quantum computer, if you want to double the power of the quantum computer, it is enough if you change from 32 qubits to 33 qubits. Just one bit will make the power doubled. So that is the speciality of this quantum bits. And other very important thing is you can do operations on all superposition, like massive parallel computation. So for example, if you see that consider one math operations on 2n numbers is encoded in the classical computers with n bits, it requires how many steps? It can requires 2n steps or the 2n parallel processes to perform the computation. Whereas the same operation, if you make use of it encoded with the n qubits, it just takes only one step. Okay, you can just maybe again getting confused. How is it possible if you have only one Maybe you are getting with the parallel computers. If everything is happening at parallelly, okay, the processing again, it can be done in one step. That may be possible. But again, how it is possible to have that is at one step? Just you can imagine a maze that is solving a puzzle of so reaching from source to destination. Okay, consider a maze. And if you are just using the classical computer, what you do is you will try all the possibilities to reach from the source to destination, having solving the puzzle. That is each of the path you will be trying it. But how the quantum computer again like looks like us like you can imagine as if you are having a bird's eye view of the image, and just having a bird's eye view, you can just look into the maze and try all the possibilities at a time and get the um, correct route to reach the destination in a matter of one step. Okay, that's how you have to imagine the power of the quantum computing. And this makes these properties makes the complex problems solve much easier by use of the quantum computers. Next, we will move on to the superposition, because we will see more insights on the superposition, because that is the one important property key feature that is being used in the Grover's algorithm. Let us say we want to put a qubit in a single bit in a equal superposition of 0 and 1. Then you can see, as I told you, this both the bits, that is 0 and 1, will be with the in equal probabilities. Okay, so alpha is equal to 1 by 2 and beta is equal to 1 by 2. So there are only two states. So equal possibility means so 1 by root 2. That's how you got this all on by root 2 and 1 by root 2 for both the states. So here the state of the qubit is represented as ket psi is equal to 1 by root of, that is equal both the 0 ket 0 and ket 1 are well existing in the equal probabilities. So this is called as the superposition of both the states 0 and 1. And this is for 2 bits. Okay. Now, this is for a single bit. Now let us see that superposition with the 2 bits. That is, if you have 2 bits, then your number of states you have is combination, that is zeros and 1 combination is 0 0 0 1 1 0 and 1. That is the 4 possible combination you have. It means that the quantum can exist in 4, again 4 super, that is 4 bits, that is here I can say that all the bits can be in a superposition state when they have the equal probability. That is, you can see that equal probability. Now again, now all these once if you have all the states, you want to have all the states with equal probability, then you can see here 1 by, and this is also possible, the zero state and existence of 0 ket 0 0, existence of ket 0 1, ket 1 0 and ket 1. You can see that all are existing in the equal probability, that is 1 by root 4. Okay. Now, similarly, you can understand that the superposition with the 3 bits. All the 3 bits, when they are existing in a superposition, then you can see here that is 1 by root 8. That is, this is also occurring. And again, all these 8 states are occurring with the equal probability. So you can have it as the amplitude can be set as 1 by root 8. Now, if you are generalizing it, then here you can see here the state of the qubit is represented as 1 by root 2 n. So n is nothing but the number of bits. That's what you can see here. How you got root 8? It is equivalent to 2 power 3. Since you have 3, it is 2 power. So that's how you have generalized here. So psi is nothing but 1 by root 2 power n of all the 8 states. Okay. Hope you have got all this superposition. Okay. So let me go ahead with the next one. that is decoherence. This is the property which you are supposed to understand, because this is the way a disadvantage you have in the quantum systems, like where you can it is leads to a loss of this coherence property leads to a loss of superposition. That is, the information is lost from a system into the environment. This disadvantage where the superposition and the entanglement are extremely in the fragile states. So preventing the coherence remains the biggest challenge in building the quantum computers. Okay, and the next is about the measurement, because though it is, we say that it is existing in zero state, one state, or like both the superposition state, still even you have to go for the measurement of the state, and this again, this quantum measure is a coherence process, decoherence process. And when a quantum system is measured, the wave function, that is the psi, okay, that is a psi is okay, God, something is missing here, okay. So it will be again after the measurement, if you see that it will be again in any one of these states. Actually, when I copied, I think some content is missing. So it is not possible to have both the states simultaneously. When you start measuring it, it will get collapsed to either to the n one of the states. That is, either it goes to measures or collapse to get zero, or it can collapse to get one. Okay, that is called as a measurement, and this happens because of the laws of law of quantum mechanism. Quantum. Then next we will move on to the quantum gates, and because this is also a very important topic, which we will be using in the Prover's algorithm, because of whatever you want to have the functions that can be realized only through this quantum gates. And this quantum gate is completely different from that of the logic gates, but you can just have an analogous, because in the binary, there are classical computers, we make use of the classical logic gates, but here we make use of the quantum gates, and these are the building basic building blocks of the quantum circuits. Again, the normalization, you can see that of every gate operation, it can be represented as unitary, that is U and transpose is equal to product of U and U transpose is equal to the identity matrix, and the number of qubits in the input and the output gate must be equal, and a gate which acts on the n qubits is represented as 2 power represented by 2 power n cross a 2 power n unitary matrix. And the very important thing you have to note is, unlike many of the classical gates, quantum gates are reversible. We will see here. Next, we will move on to the single qubit gate. And again, all these gates are again named after the scientist Pauli, so it is called as the Pauli X gate. If you come across this Pauli X gate, and here you can see that it is the Dirac notation is, when you apply the X gate to the when I apply the ket 0 to X gate, you can see that ket, it is get again can converted into or 1. Similarly, when you apply ket 1 to X gate, it will get transformed to ket 0. So this is the matrix representation of X, that is X, and this is the circuit representation of Pauli X gate. So given here ket 0, you will get the output as ket 1. Okay, now you can see here this so you all know that the ket 0, how it has been represented as 1 0, and ket 1 is represented as 0 1, and even already I have given you that what is X again here. Now once you multiply or once you apply this ket 0 to the X gate, then you can see here this is nothing but equivalent to multiply this matrix, that is 1 0 1 1 0 with the 0 1 1 0, you get it as See here, what is the output? You got just a simple matrix multiplication. You can see the output. Whatever you have applied is the input. This is nothing but get 0. And whatever you got is the output 0, 1. That is nothing but get 1. So now what you can infer from this is the poly gate is nothing but it is equivalent to a NOT gate. Okay. Because 1 0 has been converted to 1 and 1 has been converted to 0. So it is just equivalent to the classical NOT gate. Next, this is the poly Y gate, and the poly Y gate can see that 0 and it is applied to a poly Y gate. Again, you can get this get I get 1. And then here, this is the matrix representation of y, that is 0 minus I and y 0. And this is a circuit representation. And similarly, then so you get this a complex number. Output is nothing but again get 0. Since you are multiplying with this as y, you can see that you get the complex number. And the next gate is poly Z gate, and the Z gate is again the has represented matrix represented in the matrix forms as 1 0 0 minus 1, and accordingly you get the output. You can see here this quantum gates, just like the classical gates. You can just see here X gate will go for a bit flip, that is equivalent to the NOT gate. Okay. Whereas if you apply the Z gate, it is equivalent to a phase flip, because again you can see here it is a output. What you can see the output, it is a phase flip. Then a very important gate is the Hadamard gate. It is called as the H gate. And here you can see the Hadamard, the H, the matrix representation of the Hadamard gate is 1 by root 2 of 1, 1, again 1. That is actually it is, if you multiply and see, you can see that is equivalent to what you get is 1 by root 2, then 1 by root 2, 1 by root 2, and 1 minus 1 by root 2. Okay, actually it is equal to that. The probability again they are having all the all the states, either it is 0 or 1, they have the equal probability. It is 1 by root 2 and 1 by root 2. So what you get from this is the Hadamard gate is one which is called which is again the represent the superposition state. Okay. Next, then the T gate. So T gate here it has been represented mathematically. So once you get apply this T gate, you get this as the output. Then other important gate is the controlled NOT gate. So I have given again here the next slides I have given you so that it will make you understand more clearer. And here you can see here that how this get 0 state has been converted into again the unitary matrix. Once the Hadamard gate it is multiplied with get 0, again you can see that what is the, so you get the output as the superposition state. And this is one of the important gate. Hadamard gate is a very important gate in the quantum computing. And if you see that if you have again apply the Hadamard once again and then you get this as a state. Again if you apply the Hadamard, then you get the state as 1. So you can see that so actually this Hadamard gate is used to again to put the qubits in the superposition, whereas once you apply twice it leads to the flip. Okay, so it is two Hadamard gates used in succession will be equivalent to the NOT gate. Okay. Now controlled NOT gate. This is one important gate that is used in the quantum computing and which operates on the two bits. So one will be considered as a target bit and the other one is considered as the control bit. Now based on the control bit, you can see that it will have the again we will get the target bit. Now, if the control bit is 1, the target bit is inverted. Okay, so here you can see that so this is considered to be the A is considered to be the target bit. Okay, and B is considered to be the control bit. Now, if you see here, whenever the control bit is 1, according to this, how this quantum gate control not gate behaves is, when the control bit is 1, the target is flipped to the flipped. Okay, it flips to the next state, that is 0 is flipped to 1, and you can since okay, and here you can see this 1 has got flipped. Since the control bit is 1, then the target bit is flipped again, like I can see here, or inverted. The target bit is inverted, so 1 has become 0 and 0 has become 1. Now if you compare this other here state, that is when the control bit is 0, there is no change in the state here. And here also you can see when there is control bit is 0, there is no change in the state. So this is how the control not bit behaves. It is called as the CN gate. And this CN gate has similar behavior to that of the XOR gate, but with some extra information to make it actually a reversible. Okay. Now again, this is the one diagram which shows the multiplication by 2. We can build a reversible logic circuit to calculate again the multiplication by 2 using the CN gates. And if you are arranging the CN gates in this following manner, you will get the multiplication by 2. Okay. Next, we will see the other important gate is called as the controlled NOT gate, and which operates on the 3 bits. Again, only one and if and only if so these two B and C are control bits, and if both the lines again are 1, only then that is when both the bits are 1, only then the target bit is inverted. Now you can see here, this is the state where both the bits are 1. Now you can see that A, the target, it has got inverted to 0 has got inverted to 1, and 1 has got inverted to 0. Okay, and next we will move on to the, now having understood about the gates, now we will we'll make use of the gates to build the circuits. So here you can see this all this q1 q2 all nothing but the qubits. Okay, and then these x, then all these are nothing but the gates. All these are nothing but the gates, and here this is nothing but the measurement gate. Okay, it is represented in this form. Okay, and the double line represents the classical bits, because whatever we do it, ultimately when we measure, it is represented as a classical bit. Okay, now this is one example of a quantum circuit model. Again, this here this particular circuit is made up of Hadamard gates, and through 3 qubits in the input, and the output what we have got has been represented. And let me skip this, and you can see that this is again this one control NOT gate. Again, it is considered to be a universal quantum gate, whatever all we have already seen. Next, we will move on to the quantum algorithm, because the very important of again today's session we have to look into the quantum algorithm, that is the Grover algorithm. So let me go fast here. So why we go for the quantum algorithm? What is necessary? Again, because of the one property of quantum parallelism. Again, and then and because of the dimension of quantum Hilbert space, where the size of the state is exponentially larger than the classical system. The other one is because of the entanglement capability. Okay, and which is not existing in the classical systems. And because of these properties, the quantum these quantum algorithms are known to be faster than the classical ones, and very much it can be applied in the cryptography. Again, you can you might have come across algorithms, several algorithms which use of many number of bits as key bits, like if you have key bits as 1024 or so, then maybe the classical computers take very long time to break it, but the quantum computers, it will do the breaking in terms of seconds. So that's how again this same the perspective of the entire system, again it is going to change by making use of this quantum algorithm. So next we will move on to the Grover's algorithm, and this Grover's algorithm is a again and here and this particular algorithm is used for again is called as the searching algorithm. And this global algorithm, it demonstrates the capability of having the super speed of searching the given element or a given task or whatever it is in a unstructured. This is actually it takes the data of unstructured data, again unstructured search again but it can perform this task in a very superior speed compared to that of the classical system. So now we can see that the task of search problem is given a task of finding an element omega in a domain D of a size n. That is, you have given a list of a size n, then which is equal, that is n is equal to 2 power n, then it can be now if you this is the task that has been given to find, given a list, you are supposed to find as a element of the omega. Okay, now if you come across a classical solution, if you go for the brute force algorithm, what do, you check having given a list of elements in an array, what do, you will be searching one by one. So we are here we are assuming it is an unstructured, okay, search problem. So what happens here, directly you cannot apply the binary search. So what you do is you do it if the best case you'll get as one, and the worst case you have to search all the elements, and finally you'll get a, that is it will take a order of n, and if you have the average of it, have a minimum of n by 2, that is the order of n by 2. Whereas if you go for the Grover's algorithm, it provides the faster solutions using the quantum computation, and it actually the it will execute in the order of root n. That is the important importance of making use of this Grover's algorithm. So it is speed up the again then indeed it is actually a time saver of finding the items. And the quantum algorithms, if you see that there are three main steps. That is first one is the initial, that is state preparation. The next one is the oracle. The next one is the diffusion. Diffusion again, that does nothing but the amplitude amplification. The first one, setting the space, that is the first one is you have to prepare an equal superposition of all states. That is the, you call it as a state preparation. That is what you do is you make the existence of all the states in a equal position. That is nothing but a superposition. Already I've told you that if k0, k1 or all are existing, then what you have in equal probabilities, then it is nothing but the superposition. So the first step in the Grover's algorithm is you have to set the state. So that is if you are with the equal probabilities, that's why it is called as prepare an equal superposition of all n states. Okay, and then the next one is the oracle. And the oracle is the one which is oracle, that is here the oracle query is the one which is used to mark the target state. That is, you mark the target state in the sense to find the one which is correct solutions. If you are asking to find a target state is omega, then the marking of that particular target state is done by the oracle. Now coming to this, I think I do not have that oracle. Wait, let me just check. Yeah, not given. Okay. Yeah, I'll just go ahead with this. Okay. Now, if you see this, this oracle is the first step is you are setting the states in equal probability. The second one is you are marking the target state using the oracle function. And the next state is the amplitude amplification, which is nothing but enhancing the probability of measuring the target state. Okay, then the fourth step is you are measuring the quantum state to measure to, that is to find the target omega. So here you can see this how the Prover's algorithm is implemented through this quantum gates. That is, you can see that here gate 0, that is the with the bits, different bits q1 to qn, and it is applied to the H gate, that is a Hadamard gate. By applying the Hadamard gate, already I have given you enough explanation of once you apply the Hadamard gate, then you can get the superposition state of the bits, qubits. So that's how we are applying this Hadamard gate to the qubits to get the superposition. That is the first state. The next one, next step is you are applying the oracle. Okay, so this is the state where you will find, you will mark the target, that is the correct answer what you want to have. That is done through this oracle function, and then whatever you get is just only a probability. Okay, then you are going to repeat this process several times to ensure or to maximize the probability of the correct answer. That is done through the Grover diffusion state. Okay, that is diffusion operator, and here it also consists of a set of quantum gates. And finally, you go for the measurement. Now, here you can see if you're going step by detail of each and every step. Now we can see that the first step of initialization. Now, as I told you, you are applying. So assume that you are having there are n items and each are represented in the grayscale and gray color, and you want to find out one item which is in the purple color. That is the target omega. That is, now you can what you can do is you can apply this Hadamard gate to each of the qubit to create this equal superposition of the state, and so by the result you get this is the one superposition state. Next you can see that now having the next step is you are going to go for the oracle query, and this is, as I told you, it is used to mark or find out the correct target state, that is omega. Now this is how what you do here over is the oracle function. You have to define this oracle function by which you will get the solution of, that is the marked state. You will be getting the marked states. Okay. And again, the other thing is this oracle function will flip the face of the target state to negative state. So accordingly, you have to find out the function f of x in such a way that it is 0 if x is not equal to, this is the target. Again, if small x, again it is not equal to the target state. Again, it is equal to 1 if x is equal to target state. So accordingly, you have to define the function f of x. This is again, it depends on the problem or the, again, like what is the function which you are going, how do you define this function? That depends on the problems or the applications which we are using. Okay. Again, here, for example, like if you have a, depending on the problem of I can say it as assume that if you have a pattern matching problem, and then you can have accordingly you have to set the function f of x. Suppose if you have the quantum chemistry problem, accordingly the function you have to act. The function should determine that or calculate the energy levels for each of the state. And if you have the optimization problem, then the function will be again the goodness of each state. So like this, it depends on the what is that problem. Accordingly, the function you have to identify the function, and this is considered to be the black box because based on this function only, you will be able to find out the correct state or the correct answer. And then next step is the amplitude amplification, where you will be in this in this step, you will be enhancing the probability of the measuring set. You can just observe in this diagram. So having found out this as a correct state, that is the solution state, this step of amplitude amplification will amplify this particular state. That this increases the probability of measuring the target state. That's how this step is used for just to increase the probability, and this is done using the Grover diffusion operator, which is used to amplify the amplitude of the mark state. And this is the Grover diffusion operator. And if you see that steps of the Grover diffusion operator, it undergoes the Hadamard transform, and then inversion about 0, and then again you have the Hadamard transformer again, and you have the reflection about the means. All these steps will improve the amplitude. That's how it improves the probability of the success of the measuring state. Okay. And the next one, the final step, the Grover algorithm, is the measurement algorithm, which collapses the quantum state to find the target. Again, the set is find the omega, that is the target. So you have to repeat this oracle and the amplitude steps approximately order of root n times. So whatever by which whatever you get the output after the result of a repetition of root n times, you get whatever you get is the measured quantum state. Okay, and this is all about the Grover's algorithm. And advantage of this algorithm is compared to the search time, it has been got reduced in the order of that is root n. And then the applicability, again, it is useful for the unstructured search problem, and it is also it's also applied to the optimization, pattern matching. Again, you can just imagine nowadays the huge volume of data, everybody is using machine learning, deep learning, all those things. In that case, again, there you come across this pattern matching, all those things. So this again Grover's algorithm can be applied for the pattern matching, and still there is a limitation, like compared to that of the Shor's algorithm. Here, the quadratic again, it's not the efficiency is less compared to the Shor's algorithm, and very importantly, it requires a quantum oracle. That is very challenging to implement, because without knowing the without setting the quantum oracle, you will not be able to find out the correct state. And if you come across the real world application, it is the database search that is used in the applications like e-commerce and the scientific data, and then optimization problems, like when you have the again when I come across that applications, I could have told you about the scheduling, then financial modeling, then even the when you have trucks, then road finding the optimized route, all those things, it can be done using the Grover's algorithm. And machine learning task, as I was telling you earlier, that is unstructured data, and then clustering, classification, all these things you can apply the Grover's algorithm. I will skip the slides for some time. I will just get into the again, just to give you the feel of
Excuse me,
implementation.
ma'am. Sorry for the intro. So
Yes.
another resource person is waiting, ma'am.
Yeah. That's why I'm just skipping this all these slides.
Okay,
Just
okay, ma'am. Okay.
yeah, I'm just skipping these slides and
You may proceed, ma'am.
yeah. I'll just show you that. So I thought of giving go ahead. So this is one where the Grover's algorithm implementation of the Grover's algorithm has been done, and you can see here. And then whatever, as I was telling you, the steps like initialization, the execution of the oracle, the application of the diffusion operator, and then repetition of the steps 2 and 3, and the final measurement. This is how the algorithm works. And here you can see this like you can see this oracle operator, and I can this tuple is nothing but CC not gate. Okay. And so this is the code. And the circuit for realizing this oracle operator is, you can see that gates, Hadamard gates, and this again the oracle function is followed by the Grover diffusion operator, which is nothing but the doing the step of amplitude amplification. Then here you can see that this is entire code for the Grover's algorithm for searching the decimal number 6 in the database. And you can see that that's Hadamard, and then you have the oracle, and then you can see this code for the diffusion. And then this is consisting of again topology, and you can see here and this is just an emulator. Again, you can see here this is the one initial state of the Grover, and then here this is the one next one, that is the Grover, where you go for the oracle function as well as the diffusion operator. And now I can, what I can do is here so when I perform this function, apply the function, you can see that maybe in the first iteration you get the probability of 0.775. That is assume that you are getting a 77 percentage of the success of that target. That is then if you are repeating it, you can see that the success of the measured state, it is 94. Okay, so by performing these iterations, you can see that success probability again next if you are doing it, the success probability has been decreased. I can show you that by running this code, I think. Okay. So it is taking a long time. In between, I may just tell you about some, not sure whether I'll be getting it. So okay. So the meanwhile, I can so here, since it is a faculty development program, again you can create interest among the students in quantum app development, so that you can ask the students to create and deploy the applications using this quantum computing capabilities. And by which you can, for which you have to make use of the programming languages like Qiskit or Circ. All these can be used for quantum application development. And because of by which you can solve some trickiest problems, which is highly hard or difficult in the with the classical computers. That is one perspective. As a faculty, you can motivate the students or encourage the students to see in the other perspective of developing the quantum application. And the other perspective is the researcher's perspective. That is, we can. There are plenty of challenges that is there with the quantums, and even for the research problems also you can have, as I was telling you, like. In cryptography, again in cyber security, this particular again quantum computers, it can be used for creating the unbreakable codes, and that can be used. Apart from that, you can go for the drug discovery, and that is to simulate the complex molecular interactions, so that you can go for discovering of new drugs. That is one application where the quantum computer is being used. And other than that, you can have the optimizing the routes for delivery trucks, scheduling tasks. You can go for this. You can make use of this quantum computers. What is the problem? Yes. Please. Okay, you can try. I can share with you the link. You can just try at your after the session also. So that I thought that I can show you, but still I was able, I thought I can execute this and show you, but no problem. Here I have given you now. So this is what by once you are getting executing, you will be able to see this this like circuit. You'll be able to see the circuit, what that has been as a result of applying this global algorithm, how it has got applied. And then and apart from that, you'll be able to see in the result what is the success probability rate of the correct item that has been found. And if you see that in this particular one, again it is since it is here that has been considered as only three, okay, 3 bits it has been considered. And here you can see that the probability again within 2 iterations you'll be able to get some success rate are 94%. But once you go for the third iteration, you can see that the success probability has decreased. So you have to stop with that. Okay. So the number of iterations, see, that is also a very important thing that you have to set it is actually. And if you go for too many iterations, then definitely there is a possibility of the decrease in the success probability. Okay. So I think mm, so I want to conclude giving you this that showing you the quantum computing market size. You can see that how much it has varied, has improved, or that from 2021 to, I can see that the state of market size of quantum computing in the year 2030, it is 125. Okay, and 125. Okay, that is the advancement you have in the in the in the area of quantum computing. So with this, I want to conclude so that you can focus again. This is again quantum computing is giving away the future. How again you can observe the having seen this market size. Um, Quantum tech is the wave of the future. By diving into this field, you are getting ready for just like getting into the thrilling roller coaster of tomorrow's tech world. So with this, I stop my presentation, and if you have any questions, you can ask.
Dear participants, if you have any questions. Thank you so much, ma'am, for presenting such a valuable and compelling session. Really, it's very informative, ma'am.
Okay, if there are no other questions, let me take this opportunity to thank the organizers for giving me this wonderful opportunity and sharing the knowledge, whatever I have with all the participants. I thank the coordinator, Dr. Srinivasan sir, as well as Dr. Chandrasekhar sir, as well as the management, the principal of PSV College of Technology, and I thank as well as Vinod for was guiding me again in helping me in setting out the session. So
Thank you so
thank
much.
you, thank you everyone. Hope you have got some insights of this quantum computing. I'm really very happy to get your feedback also. Thank you all.
Thank you, ma'am. Thank you
Thank
so
you, ma'am.
much. Dear participant, the session 3 feedback link is available in the chat box. So kindly take a moment, fill out the feedback form for the session. Dear participant, use the chat box responsibly for the questions
Hello.
and relevant discussions.
Hello.
Yes, sir.
Sir, I have a question actually.
Ma'am.
Hello.
Ma'am? Yes, sir, please.
Yeah, madam mentioned something like Oracle in that Grover's algorithm.
Okay, sir.
Could you please elaborate it? I didn't get that. I mean, I could not really follow her at that point. If you don't mind, please. Ma'am is available there?
Ma'am, are you there? Sorry, sir, she's left, I think so. So just we will contact soon.
Okay.
Can I
I will
carry on?
contact her.
Ma'am, ma'am
Madam.
is there.
Yeah, madam. Can you
Can
hear me?
Yeah, I can hear
Yeah.
you. You can just get to know here, or actually the second step after the
Yeah. Second steps.
after the initialization is the oracle function. Okay, so this is
Yeah.
nothing but you are finding out a function which leads to the correct solution which you are supposed to see. Grover's algorithm is meant for finding or searching a particular target value, right? So this particular oracle step is you are setting out or designing a circuit or a function which leads to a correct solution or find out the correct solution. So assume that you have a function f of x. If you want to find out then seventh or sixth, here in this example, I think the input is the 110. Okay, and if you see that and here if you are following this circuit, now already I have given you the what is the function of each of the gates, right? Now having how whenever you are designing this particular the way how you build the circuit, it should lead to a lead to a result in such a way that it marks the correct function, correct solution.
Yeah, madam. My question is basically like this.
Mm.
We are dealing with a superposition state now.
Yeah.
Yeah, so the choice I mean the target that I am looking at and the target
Mm.
somebody else is looking at, that
Yeah.
will be different. Yeah, so this oracle, how I mean, is it common for both of us? I mean, if we are searching something.
Yeah, because you know the target value, no? See, this is here in this example, if you consider, it is not you or me. The target value which you are setting as a that is the omega. You have to define a function, generalized function. See, when it will result in 110, then again whatever the target will, accordingly this circuit has to be
Yeah, that
designed,
is uh,
defined.
a problem specific, I think.
Yeah. This is meant only for searching. So depending on the again depending on energy levels, that also differs. Yes,
Yeah,
true.
that's what. Okay, thank you, madam. Thank you for that.
Hi, ma'am. Hello. Hello.
Yes.
Sir, ma'am is available, sir. The session 3 feedback link is available in the chat box. So participants are requested to submit daily feedback of the session. Sir, can you please stop the screen, sir?
Vinod, you can start. Shobna ma'am, are you available, ma'am?
Yes, sir. Yes, sir. Yes, sir. I'm here.
Yes.
Dear participants, we move on to the next session. So it's my great pleasure to welcome Dr. P. Shobana Prita, software developer at the Brainswing Educate Private Limited, Chennai. So Dr. Shobana Prita is a highly accomplished individual and recipient of prestigious Young Entrepreneur Award presented by Aram Foundation. She is also the founder of Shobana Educational and Charitable Trust, showcasing her commitment to the educational and social causes. So we are truly privileged to have us today. So on behalf of everyone here, I warmly welcome you, ma'am. So we are eagerly look forward to your valuable insights in today's session on implementing the quantum Fourier transform and Shor's algorithm. Welcome, ma'am.
Yes, ma'am. Thank you, ma'am. Could I proceed, ma'am?
Yes, ma'am, you proceed.
Yes,
Yes,
ma'am. You can share your screen.
Yes, sir. Yes, sir. I'm sorry.
Yes, ma'am, visible. Can give full screen.
Screen is sharing, sir.
Yes, ma'am. Okay. Now, okay.
Yes, sir. A very
Yes.
good evening to all of you. So before I would start my session, I would like to convey my thanks to all the dignitaries who were welcomed me for this FTP session, and also to a very a warm wishes to everyone who were presented here. And there is a session between not to between, it's about to be quantum computing and to be algorithms of the computation. I like generally if we just move on to quantum computing, which is trendingly moving on, because everybody we feels that like the how do we commit this commit the work and to be as very shortly, or else how do we complete the work and to be as very automatical manner. So this is what we are expecting, even to be right from the kid and from the elderly persons. Everybody will think that. So how do we commit the work and to be as shortly? How do we complete the work and to as shortly of that? Okay. So this is what everybody feels that. So if we feels as like that, so what kind of thing that we supposed to go for easy computational or to be a computing methodology that we are expecting to go for and to be automatical manner, right? So even though if we takes for the example of like to be computing into the shortest manner, we takes that is quantum, call it as 0 and 1s, we can take it as to be commit with as very shortly. For example, if somebody will ask you the task, or otherwise commit you the task for to multiply the two numbers between any two numbers, to take off any two numbers to be multiplied, we can multiply easily. If they are asked to do it to multiply the number and reverse it, if they are asked to do it to multiply and reverse the number, to which two numbers we multiply and to get this answer. So likewise, if they give you the question, so by the time we just think of a few minutes and to be work out as take part of the time to work out, right? It's name called a factorization, we can call it that, right? So those kind of things we can have into be a different manner of them. So likewise, we can mention as to be a quantum computing. So we have certain algorithms, like certain algorithms call it as to be certain formulas we have. Like how do we follow those kinds of formulas and how do we follow those kinds of computational methods, everything. Okay. So here we are going to start with the first thing that's name called for Murray's law. And that Murray's law, like to be call it, like what do we say to be shortest manner of that and to be a Murray's one. Okay. To be to observing the number of transistors, like to be, we all may know that to be work which comes into be a integrated manner of that. So that too will be comes into be a like a certain principle to be follows that, right? So this is not to be actually scientific law actually or proven theory actually. This is only to be relationship with to be a projection of history. Okay, so this will be which shall be commits with some prediction method which shall have into be constraints. For example, there is a transistors which will have into observing the number of transistors like according to the year or according to the methodology, like what it is happening. Okay, which is coming to be a components which is integrated into be a circuits. So likewise only we are taken into be a microchip methodology which is taken into be a decade method one. Okay, so like since we taken off a Murray's, like as I told you already, which depends on the number of transistors and which is integrating with the double of every 2 years will be coming. Okay, that is named for, that is actually which is happening, minimal rising into be a cost of work. Okay, so like we are falling into be a trend as to be automatic scale which is happening into 15 to 20 years. So which that happening into 15 to 20 years, which was into the quantum as to effects with mechanically as to occur the scale of measuring the state. For example, the position. Okay, the position or the measuring the state which could works with the to be different perspectives of the two. It would be disturbs into that. Okay, so actually the quantum system which may have into sometimes it to be behave into be several states of the work. Okay, not only single state shall works with the several states of the work, and that several state which will be monitoring into the different perspective of that. Okay, so here the mechanical effect. What is the mechanical effect which shall be here? The mechanical effect to be additional nuisance to overcome, or new types of behavior to make use of that. So what is the thing that we supposed to be make use it or to be overcome it? That we supposed to go with the wider manner. So how do we go with the wider manner? Like let's see, there is a short 94 like to be a polynomial time algorithm. So that is named called factoring the integers. So factoring the integers, which is very simple. So nowadays the kids are doing it to be a factorization, to be taking out from the using of the coefficient value, to be taking out from the different thing, or I mean to taking out from the different a value, or to be a as what is the equivalent term of the value that they are taking out, right? So as well into be a algorithmic pattern, they would have some formulated one. Using the formulated one, they can get some integers category of that. So that could be break into be existing of public key of a crypto system. That will be including with the RSA and elliptic curve crypto technology. Okay, so we do have those things with that. So next thing is probably and to secure codes with the short keys. So what is the short keys to be commit with that? That short key will be like comes into be a as we used method, like to be a those kind of information, like to be the algorithms which can takes into be a faster manner, and as well into be a combinational methodology. So as like that we shall use it and to be finding a problem or to searching a problem of that. So this faster algorithm for simulating the quantum mechanics. So it could be simulating the quantum mechanics which will have into be a different turns of them. Okay, so for example, communication saves the distributed system. So as we all following the distributed system which we have into that, so that distributed system restricts into be which takes into be a as different manner of the work. So let's see on one. So it shall be a very efficient to be proofs of our systems, like that kind of efficient system, like how it could be works with it. The quantum information theory that we have into separately, as we call it as in generalizedly, like there is a classical information which can follow use it to be a probability theorem of that. Either to be tossed the manner, either to get a head or to be tail. We'll get only the head or tail. I mean 0 or 1 only we're supposed to get, right? The same thing of to be here, the classically informed the theory which shall be comments within to be a quantum. Next thing is, what is quantum computer? We may all just like blabbering the word of called quantum computing. Actually we supposed to wants to know like what, like, excuse me ma'am and sir.
Yes, ma'am.
And the PPT is not visible
Yeah, it's visible, ma'am.
because one of the madam have dropped the chat box. The PPT is not.
Yeah, it's visible only.
It's visible, right? Yes, sir. Thank you, sir. Yes. Sorry. So a quantum computer actually it's take it as a machine that can perform into be a calculating machine, and based on the laws that we can follow of the quantum mechanics. So which shall have the behaviors of some particles and which shall be in some subatomic levels. Okay. So for example, that we can start from the introduction. How does it we start with that? Okay. So that is the thing. I think I can safely say that nobody understands quantum mechanics. So that can who can say that, like Feynman have said that about in 1982 we have been proposed like idea of creating machines based on the laws of quantum mechanics instead of laws of classical physics. Okay. Like after that 85, after 82, 85, the David sir have been developed into the quantum Turing machine. Okay, that could be shows into the quantum circuits level, circuits that shows into universal pattern level. Okay, and after that it comes into 94. The 94 it come up again to be a quantum algorithm to factor of every larger number values of a polynomial time. And next after a 94 there is a 97 which develops the quantum search algorithm, which shall have into be root and complexity of the work. So they shall start with that. I can start with, I think, with a safely that nobody can understand. That will be elaborating from the 82 to 97. They were elaborating and they were finding out into the different techniques that to be, promote with that. Okay. This promote will takes into a representation of data qubits. Okay. The data representation of data, like first thing is how we do represent the data. A bit of data shall be representing that single atom which shall have into one of two states, and that could be denoted by 0 and 1. That single bit that shall be forms with a qubit. Okay. And next thing is a physical implementation of qubit could use the two energy levels of an atom that will be excited to be stating the representing the value of 1. That ground state will be representing the value of 0. Okay. If there is a 0 value state 0, you just look on here. There is a nucleus which is being here, the electron which is being here. And there is a 0th level. We shall start with the ground state. Excuse me, sorry. Starts with the ground state and to be like excited state, which the light pulses have been frequency have to travel the time. There is a time travel between the two things, which will start from the ground state to be a excited state. So that should be comes within the state 1. Okay. Next thing, the representation of data, the superposition. Clearly, we have seen a qubits, and now it shall be moves into superposition. Each and every single qubit can be forced into be a superposition of the two states, which is denoted by the addition of state vectors. Okay, so not into like to be a local vectors, it shall be a straight vectors. That straight vectors which is to be here as a formulated one to be here. So there are two complex number which shall be mentioned here, like to be like alpha 1 and alpha 2. If it takes that will taken into be square, which is equivalent to 1. That with superposition, which shall be takes into be a two different states of that two different state which comes into a same state level of that, it takes into 1 and 0 at the same time. Okay, this is name called it to be a data separating. Actually, next thing is, so data superposition, representing a data superposition, which shall have the major thing is to be considering the 3-bit of that. Okay, so previously we have seen it to be a 2-bit category. And now they're considering it to be a 3-bit category register of the unequal weighted position of the possible values. That unequal weighted of the possible values could be denoted into the perceptions value, which is mentioned into be a light pulse of frequency added with the time travel by that. Okay, which is we are taking from the time traveling, we are taking in a 2 category of a value, right? So that we are just taking part of the value divided by 2 of the superpositioning. The value shall be positioning that. Okay, value shall be positioning to the next state of the work. Next, there is a 1 qubit. So what does it call it to be a qubit, and what do we say to be a 1 qubit in the sense like which will rotate into be a mathematical abstraction, which they could have into a 2-dimensional complex vector into be a space and Hilbert space of that. Okay, this space and Hilbert space into be a like a Decoherence notation. That notation will be called it into be a column vector as well into be a row vector. We shall have into 2 category of vectors. That 2 category of vectors which takes part into be a dual vector. Okay, that dual vector to be a transpose and complex conjugate level of the word. Okay, if we realization of the qubit that we takes into be part of first thing is nuclear spin. Okay, that nuclear spin which takes into positive or negative. That positive or negative which comes into be a polarization method of left or right of it. Okay, this shall have into be a electron state. As I previously have displayed you, electron state into be ground level into excited level. So 2 level of categories which 2 haven't, right? So this is what to be called it as 1 qubit, which shall already mentioned to be a mathematical abstraction. The vectorization into be a 2-dimensional complex of the vector method. Okay. Next to be a bit versus a qubit. So the a bit versus a qubit, a bit is to be 2 distinct states of the work. So that 2 distinct states which shall have it to be 0 and 1. That measurement, it doesn't affect with the state, but it will have to be the bit of this category. Okay, that bit of a category to be qubit, which the level can be state into be a one state into another state, which shall have it be linear combination of base state of the work. When we measure the qubit, we find it the state 0 with probability of the alpha 0, and the second state 1 and 0, and then that 1 probability takes into be alpha 1 square of it, which shall have a complex number. When do we feel the complex number? Where we excited to see the complexity to the work, so that time we can feel that it's a complex category, complex number that we supposed to be categorized to 1. Okay. Next one, the Bohr's sphere representation of a 1 qubit. So how the 1 qubit have been to be representing into the superpositioning vector? They're connecting the center of the point, which is of a probability of a 2 amplitudes of them. Which the 2 amplitude is expressing into that expressions that expressed into the Euler's angle of the work. That Euler's angle can be expressed with the 2 different probability of the amplitudes. And qubit measurements which shall be have into be a that qubit measurement like first starts within a one bit. That 1 bit it's equivalent, it takes part into be a 1 qubit. This is what to be possible states of qubit which before this measurement. This statement of qubit after the measurement, how does it to be? Just look on that 1 bit which is taken into 0 and 1. That 0s and 1 which is being mentioned into be superpositioning method, which shall have into be a basis of logical state which shall be a 0 and logical state of a 1. That 2 things will be commit with the or connect with the 1 qubit. Next thing is with that 1 qubit will be elaborating the state of the measuring the elaborating the state of qubit of the thing, which is to be developing into 2 categories of them. This is to be a qubit measurement which is being mentioned here. Next things, 2 qubits. So 2 qubits which will be representing vectors in a 2-dimensional thing. So 2-dimensional Hilbert spaces with the 4 basis vectors of that. So actually we will have a possibilities 0, 0, 0, 1, 1, 0, 1, 1. Obviously we will have and takes part of the 0s and 1. We wanted to make it into be a probability as a possibility probabilities, right? So possible probabilities are 0, 0, 1, 0, 1, 1, 0, 1, 1, right? If we take this possible probability, we should take of it. It shall be comes into be 4 different basic vectors of that. So, but which shall works when automatically or which shall works to comfort with all the number. It's obviously we may all know that 1, 0, right? So this 1 and 0 only we may all know to be declared of a thing. And when we measure a pair of qubits, which shall be desired into be any 4 states, we can take of any 4 states. That any 4 states can be come with it. that any 4 states which shall have into be a measuring of a probability states of that probability states which shall commits with the alpha square alpha, I mean, it takes part of the 0 0 0 1 square 1 0 square 1 1 square. If it combines with the complexity manner of a probability which shall works within the same category of to be a 1. Okay, so like how do we bring that measuring that? So we do want to measure. So we do want to measure before the measurement, the state of a system will consisting of a 2 qubits, which the 2 qubits will be uncertainly given by the previous equation of the corresponding probability. So what do we have? The probabilities which will have to be correspondingly, and that can be takes part of that. So after the measurement, the state is certainly works with 0 0 0 1 1 0 or 1 1, which is a like case of classically 2 bit system. Okay, so with this 2-bit system have to continue, like first bit qubit can be observed, only the thing. So 1 qubit which conclusions offer can be, we can draw that. Okay, so that what do we expect the system to be left uncertain state? So that could be work within measure the second qubit that can still be the continuum of a states. The first qubit can be 0 with probability. Second qubits can be comes with 1 with the probability. 0 with probability has been comes with the alpha 0 plus alpha 0 1, and 1 probability which shall comes with a 1 0. So obviously we may all know well of the 1 0 can be commit the work with as workly, and then as well it will be a 1 1. So this is what it will be measuring 2 qubits of the continuations. Next it will be a Bell state. So the Bell state which shall works with 1 squared of 2, and that 1 squared of 2 which will start with 0, and other squared of 2 which will start with 1. The measurement of qubit and state gives it to be a 50% of time to be works with logically. That logically which shall denotes into be a plus, that denotes pattern, call it as into be a Bell statement or Bell state we can call. Okay, next thing is entanglement. So which is being needed of entanglement. Entanglement is an elegant one actually. This elegant one almost the exact translation of German term, like that German term can be used by the Schrödinger. Okay, who was the first to be recognizing the quantum effect. Okay, actually we wanted to recognize the effect to be work with or to be continue with it, right? And next thing is entangled pair. We may all know that what is a tangle. Okay, right? To be taking out clarification, I mean clarifications of that which we were as messy of tide, right? So we, by the time we are doing entangled, right? So there is an entangled pair of single quantum, which will be a position, superposition of possible states, which is equally manner. That entangled states which contains into no information about the individual particles. That about the individual particles can be liked within to be a different individual turns of that. That important property which is entangled with that one particular influences, one particle of influence which will state with other influences also. Okay. And next, Einstein call it as spooky action at the distance. Okay. So which shall it be a spooky action at the distance, and that distance will be measuring off to be a some like certain state of the one. That certain state which is to be entanglement, one thing. Another one is the operations where to supposed to be commit. Okay. So reversible logic and due to the nature of quantum physics. Okay, so there is a destruction of information in a gate because of heat that will be evolved, which can destroy the superposition of qubits. Okay, that superposition of qubits can be accessed with, so it to be heat evolved or to be destroyed. Not to be destroyed, the superposition of qubits of that. There is an example which can take for the AND gate. So the AND gate, which to be 3 cases of information, is being destroyed A, B, and C. So this A, B, and C, if it takes off a 0, 0, take part of an AND gate, using of AND gate, 0, 0 comes into 0 of that, right? The same thing, 0 and 1, output is to be 0. Why? Because we all know well, when there is a true states are there, we may get off to true state again back, right? It's a quantum gates. This is not a type of a gate, cannot be used over there. Actually, it's to be a quantum gates shall be used over here. Okay. This is named called to be a reversible logic, which is being into be a qubits operations. Next, quantum gates. So what it does produce, what it does shows the quantum gates of that. The quantum gates are similarly to classical gates, but do not have it generate. I mean, do not have the to degenerating the output. Okay, if it is not degenerating the output, that the original output can't become, right? which will not be derived one also to be. That derived one uniquely happen. They must be happen to be a reversible pattern. Okay. This means call it as deterministic computation that can be performed with the quantum computer. Only it's reversible. Luckily, we may have many deterministic computation can be made into reversible, right? So that can be says into which Charles Bennett. Like luckily we may have, or luckily it may shows that one, right? This all comes into be a quantum gates over here. Next, how do we mention one qubit of here? Okay, so that one qubit which is states into be a G is equivalent to G11, G12, G21, G22. We can make it into be a 2 cross 2, right? So one row and two row and two column, 2 cross 2 matrix which is being given here. With this being 2 cross 2 matrix which is equivalent to be a alpha. I'll take this into be clearly, right? Mention into clearly, so that will become multiplying with a different manner of the strategy of the work. Okay. So this one qubit gates to be identity gate to be qubit unchanged data. X or not gate. Okay. Shall have it to be X gate or not gate to be transposed the components of that input qubit. Which will happen to be an input keyboard, and that will be comes into Y gate. Signs into the qubit. That flip sign had mad of the gate, which is considering a part of the work. 1 second, there is an internet connection. Okay, sorry for the interruption. So there is this Hadamard. So what is a Hadamard, which will have into be simplistic gate involves into one qubit, have to call it as to be Hadamard gate, like to be a square root of NOT gate. Okay, we used to put qubits into be a superposition manner. That superposition which comes into be a 0 and 0 plus 1 and one state we can call. Okay, there is a two Hadamard gates which is used in a succession, can be used into be a NOT gate of the method one, and starts with a 0 and the 0 plus 1 and 1. We shall have to be a different category of the work. Okay, so this different categories, like it to be a controlled NOT. Quantum gates are controlled NOT. The gate which is operates into be a operates on two qubits. That two qubits is called into be a controlled NOT, and I mean call it as CN gate. Okay, call it as CN gate. That is bit on the control line, which shall have to be 1. That is invert the bit on the target line. The target line inverting the bit of the work. That inverting the bit of the work, A target shall have it to be A dash and B control which have it to be B dash. So you can see the input of the A and B are there. If there is a A and B to be two category to be false state, the same output also have comes into be a false state only. Okay. And the second thing is like to be 0 and 1 as there, and 0 and 1 which will have it to be opposite, I mean the false state which will have it to be using of XOR gate of that the 1 have been come, and either to be 1 and 0, then 1 and 0 have been. If the two inputs are to be obviously 2 and there is a target position which will have it to be a control, CN gate has been used a similar behaviorance of XOR gate. Which shall have to be CN gate methodology. That CN gate methodology will have to be work. This example of operation will have to be multiplication by 2. So multiplication by 2. This multiplication by 2 using CN gate arranged into the following manner. What kind of a method that we supposed to be following is to that? Like what do we say? Like carry a bit, one bit value of that. Okay, that is to be input state, and that takes out into the output category, which shall have to be a carry bit and one's bit into be one's place into another place of the third. So you can see that previously. like, so I'm just carrying the ones bit into be another bit, like into be here. Okay, so carry bit into be ones place of that. Okay, so you can see that how do we use, I mean, what is the, how do we use CNN category of that? The gate which is operated the 3 qubits, which can call it to be a controlled knots, I mean controlled knot. We have seen it, right? Here, which shall be mentioned here, CCN, like to be controlled not gate of that. If the bits into be a both of control lines is 1, and then target bit is inverted, then we can comes into be that. For example, there is a target A and control 1, control 2 is here. So B dash and C.
Your screen share stopped.
1 second, sir.
Yes.
So does it share, sir?
Yes, ma'am. Yes.
Yes,
I
sir.
can see the screen.
Yes, sir. Yes, thank you. So there is a the bits which can control the lines for both the lines, which that to be inverted or to be directed point. The targeted bit value have been represented over here. Okay, so here we have been taken as a control double C. I mean double C have been taken as 3 qubits, and clearly we have taken as a 2 qubits. The 2 qubits have been performed into be 2 different strategies of the position of the work. That can be levels in that work. Okay, so this can have into the target bit into the inverted strategy of the line. So this inverted strategy of the line can be works with universal pattern. So we shall check how do we work with universally quantum computer. Like CCN gate has been shown to be universal reversible logic, which can have used by a NAND gate of the work. So the NAND gate, which shall have into be target and target control 1 and control 2. When our target input is 1, our target output is the result of a NAND of B and C. Okay, that B and C which shall support as well into the output. That input and output which shall comes into be 0 and 0. I mean 3 categories we have taken A, B, C. Then A, B, C have taken into be starts with the 0. Because we have already mentioned like to be 0s and 1 combination have been used to over here, right? So accordingly, we shall supposed to view the target input is 1. Our target output result of a NAND have been performed into be B and C. Okay. For example, if it takes off to be a 1 into be A, so that will be performed into B and C of the target value. Okay. So target value into be B and C, which will have to be taken over here. This is name called into be universally that logic has been happened into be in common methodology turn of them. Next, classical and quantum system over here. So classical and quantum system, which is called it as probabilistic state and to be a quantum states over here. So probabilistic states, which can call it as to be a, so like summation of px is equal to 1. So there are many turns of the px of that. If we take into 2 qubits, that 2 qubits which will be comes into be a 0, 0, 0, 1, 1, 0 and 1, 1. We have taken the 4 categories and 4 combinations of the one. And then next thing is if we take the 3 qubits, the 3 qubits which will comes into be a 0, 0, 0, 0, 0, 1 and 0, 1, 0, 0, 1, 1, 1, 0, 0 and 1, 0, 1, 1, 1, 0, 1, 1. So the 3 combinations which are supposed to use for the probabilistic state. This probabilistic state which shall brings into be a quantum states of the work. The quantum states of the work we shall use for here summation of px is equal to 1. But here, summation of ax square, I mean alpha x square is equal to 1. So we're supposed to prove probabilistic is equal to be alpha. Okay. So according to the condition which they mentioned over here. Next thing. There is a like a Dirac notation which will have into be a, we have taken for the basic category, like so basic like basic vectors we do mention of that already, like 0, 0. I mean the value of the 0 comes like 3 qubits we have taken for the 3 qubits using of those algorithm which shall be follows into the summation of alpha x and the alpha x value have been represented into the work. Okay, this representation have been used to be a common generic term. So this common generic term has been represented with the work strategy. Okay. So this work strategy, which can be here, like into be the key, the ket, which shall be denotes to be the column vector, which shall have to be example of convention. The convention which shall be a 1, 0. Okay. There is a one column only, not to be a row, because it name it as column vector. If there is a column vector, we're supposed to use only for the like to be a one column of row only. Okay, that is named to be a ket notation of here. This ket notation can be converted with to be another term. So let's see here. So BRA always denotes into be a row vector only. This will be conjugate of a transposing the data. So transposing the data, which is to be the row is transposed into column, the column is transposed into row. So that is to be transposing of a data, which will have into be denoting the value of alpha 1, alpha 2, which takes into be till alpha n. Okay, so this is name called into be a ket notation or BRA notation, we can call. Next, there is a bracket. The bracket which will have to be inner product level. That inner product level like to be denotes it to be a theta and to be a BRA conversion, and which will depends into be a inner level into the outer level of the over here. So there is a basic operations. We can recall the column which is being mentioned here, 1 and 0. That 1 and 0 and 0 is in 1. If it takes up 0, shall comes into 1 and 0. If it takes 1, that will comes into be a 0 and 1. It's a recollection. We just recollectioning the data again back. So there is a initializing the qubit over here. I'm just initializing the qubit here as into be a 0 and 1. 0 or 1. Okay, I'm just applying a unitary operation which shall formally used to be conjugate the transposing the work. So as we know well as the schooling of all like to be studies higher studies, we may all know about them trigonometry functions and ratios over here. So here we are going to be rotating the state of theta. I'm just rotating the state of theta and cos theta and into be a minus sine theta. That sine theta and to be a cos theta. Like to be rotating the transpose function actually. Okay. So how do we transpose that? So there is a row, it takes into be column. Column shall takes into the row, right? So here there is a sigma x is equal to x is equal 0, 1 and 1, 0. If it takes the two row and 2 column, the mapping 0 to map with the 1 map with 0. Okay. So this is what which is operating the qubits, basic operations on the qubit thing. Next thing is phase flip. So phase flip is sigma that is equal to z is equal, and we are facing the turn of cos theta minus sine theta and sine and cos theta. Okay. So that will be reflected to 0, 1, 1, 0, 1, 0, 0, minus 1. Because we are conjugating the transpose of the work. So we are transposing it as well to be, we are mapping that. So once we are mapping, we are just mapping over here and we're just mapping here. Okay. Next. Basic operations of qubits. So which shall be doing the basically operations of qubit. That shall be to be a more examples of to be a unitary operation. That unitary operations have been works with the rotationally Hadron map. That h is equal to 1 by root 2. That 1 by root 2 of to be 1, 1, 1 minus 1. Which is a combination of zeros and 1. This zeros and 1 to be rotating a data, rotating a theta function that reflecting the line over here. Okay, where it's reflecting, like it's reflecting into B 0 and 1 here. Okay, this reflection has been worked with here. So just look on here. So I'm just reflecting the data. Actually 1 by root 2 and the 2 row and 2 columns, right? So I'm just taking up a separate thing. Like 0 plus 1, which shall takes into be 1 by root 2, 1, 1. And 1 by root 2, 0 and minus 1. And there is a plus 1 and minus 1, which will have this. So this is off to call it as Hadron map. Okay. Next thing is to applying a standard measurement. The standard measurement, which shall state into be a quantum state, collapses into 0 or 1. So with this 0 or 1, that will 0 will have a probability alpha square, 1 will have a probability beta square. This alpha square and beta square shall commit within to be a 1 column and 1 operator from 0 here. So these two categories will be mentioned into the standard measurement of the thing. This standard measuring a thing which is to be existing of other quantum operations, which they can call simulatedly by aforementioned of a types over here. That aforementioned of a types over here. Let's see of the what are the things. There is an example which shall using to be BRA orthonormal basis of the work, which shall respect with the measuring the turn. So that respect with the measuring a turn, which shall be distinguishing the two states, shall have it to be a states with 1 by root 2 0 plus minus 1 and negative over here. That will be distinguishing into be a two category of two. There is a question number 1. Can we distinguish the two cases? Yes, obviously. So there is a distinguishing procedure is to apply H measure, and this will work with here. So like 1 positive, which shall have it to be 0 and minus it to be 1. So that will be here 0 and plus. So there is to be not orthogonal turn. It is not to be perfectly distinguished, but statistically it will be differentiated the value. Why? Because to be detectable turns shall be works with that. Next, there is the operations which is being here, n qubit states. The n qubit states which will have to be unitary operation. The summation of x is equal to and universal state of the work. So which shall have it to be summation of work and universal state of the work that comes into be a 1. And measuring a state summation ax divided by x. That ax divided by x takes part into be a 3 qubits, right? Because finally we have taken the value of the 3 qubits, which shall let to be a 0, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, as the probabilities, as the possibilities have been taken over here. Okay, those measurements can be used with it to be a n qubit states. We can take n number of turns, but the possibilities must be work with it. Okay, the quantum state has to collapse, but we need not to be allowed that into be collapse. Like we shall gives promoted to be a possibility of the turn. Okay. Next, the entanglement. How does the entanglement have been worked with it? There is a 2 qubits which are in states like name call it as to be alpha 0 plus beta 1 and alpha dash 1 alpha dash 0 plus beta dash 1. So this will take it to part of tensor product. The tensor product which shall be combined the system to be state within a one perfectional category. That one perfectional category to be alpha dash to be 0 values and zeros and ones. So with the zeros and ones or 1 0 or 1 1, this should take it to be a beta turns of the work. And there is a question, what are the states for the individual qubits can be works with them? Okay, so there are many states to be works with the individual forms of that. That individual forms which will be happen to be a categorized into be works. That categorizations of that, like 2 questions they have been mentioned over here. These 2 questions which will be your answer for the first one. Like to be 0, I have been applied and 0 and 1 I have been applied, 1 and 0 and 1 1. So it does to be happens work with only for an individual qubits. So individual qubits, what it's supposed to take of the one shall takes every turns into be a second position of the value. The second position of the value have been taken. Then let's look at the second one. Second one, what is the answer of that? 0 0 1 1. So what is that? It's a name called entanglement. Actually, the second state have been worked with into be second state 0 and 1 only. Okay. Possibility of the zeros and 1 only we have taken, right? The zeros and 1 only we have just supposed to give it to the combination of the value. Next, there is a structure Mohawk subsystem. So what is the structure of Mohawk subsystem? Like subsystem which can call it as qubits. The qubits which will have it to be comment 1, a hash 1 and a hash 2, a hash 3, hash 4. That will be called it as into UVW. That UVW which are meant called unitary operations. That unitary operations were to be measuring the values, measuring the turns of the work, which will have into among the value. So among the value it shall be measuring. Like this is name called, this is the displays of this quantum circuit, which will be the combinations of the value. The combination which will have into computation. Computation is to be a feasible turn circuit size scales to be very polynomially. So we just look on that 1 qubit gate. 1 qubit gate which shall have it to first starts with the BRA method. So BRA is equivalent to alpha 0 and alpha 1. So it takes into be a alpha dash and alpha 1. Okay. So that 1 qubit gate is equal to G is equivalent to like G11, G12, G21, G22. Okay. This we suppose takes into be a what to say to be a matrix methodology. That matrix methodology can takes into be a alpha 0 and alpha 1. Okay. So 1 qubit gates into be a G11, G12, G21, G22. Okay. So this shall suppose to takes with to be a matrix. I mean to multiplying or to be taken of the power of combination matrix to be works here. Okay. This part of combination matrix like G11 to G11 and to be G12 to G12 to G11. Okay. First row, first column, and second row, second column. Like first row, first column, first row, second column. Again, second row, first column, second row, second column. As well is supposed to take part of the value and to be added with that, and added which comes into be identity the value of the identity of 1001. As well, it's supposed to come. Okay. Just look on here. This is the identity transformation. So, which the identity transformation into the Paul matrices of that Hadamard Paul matrices like looks on here. To be we shall displace into be a identity transformation which shall have it to be 1001. That this could be happens into be a 1 minus 1. Okay. So here Hadamard we shall have it to be represented to be 1 by root 2. That 1 by root 2 takes part of the value of 1, 1, 1, 1 minus 1. Okay, so this is the third which will have to work with this. There's a tensor products and outer products. If it takes our tensor products, how it could be relaxed, and if it takes the other products, outer products, how does it to be relaxed? Okay, so which will be when we works with two category of the work. One is to be 0, 0, and 0 multiply 0, and 1, 0, 1, 0, 1, 0. Okay, if it takes this is the product will be, and the product category which shall takes for here outer product. Okay, so here we may mention over here one column of here and one row of here. This one row and one column which shall be like to be like example this one column and this one row shall be works with to be all together of a matrix over here. Okay, this matrix into be actually this is called it to be tensor. This is called it to be outer products. So the tensor can be works with the level of the work and it will be displaced to be outer products of the work. Okay. And this C naught to be 2 qubit gate of that. So C naught to be 2 qubit gate. This is to be a control, control input of that. This is a BRA method. This BRA takes part into be a value of a qubit. And here it's to be a targeting input value, and that will be adding the module value of that. Okay. If it takes the two inputs, that is called it as control and target. This control qubit is to be transferred into be output. So this transfer outputting transfer targeted into be qubit. Okay. So this unaltered value control into be flipped control of the one. Either if it takes 0 or it takes to be 1. Okay. So likewise, we supposed to handle over here. Next thing is C naught. So C naught, V C naught is equal to BRE. So BRE multiplied with the theta value shall be C naught to be comparing or to be computing the work with the C naught. The C naught will be G C naught and B C naught of the work. The G C naught will be the rows and columns. That rows and columns which will be appear to be a first row, first column, second row, second column. As well, the rows in category wise it shall be appears. So this here the two input qubits we have been taken. Two input qubits we have been taken. That two will be combination to be worked with to multiply with the row and accordingly to the column. But it will takes into be a BRA method and as well into be a theta of over here. So here alpha 0 and that alpha 0 which comes into be alpha 1 and beta 0 which comes into be beta 1 over here. Okay. So that will be combinating of the work. So this combination of the work shall be has it to be a alpha 0 and beta 0 and alpha 0 and beta 1. There is a combination 0, 0, 0, 1, 1, 0, 1, 1. As well, the combination is supposed to handle this. And there is a 2 qubits. So 2 qubit gates which shall takes it to be the pair of combinations of the probability state. The pair of combinations of the probability state of a 0, 0. Okay. So here the combinations have been given. This is the one state. This is the one state, and this is second state here. Like this is second state, and this is third state, and this is fourth state. So it shall be a 0, 0, and 0, 1, and 1, 0, and 1. I mean 1, 1. So we are just probabilistic the turn of that using of a two different pair of value. That two different pair of value we are taking into be a identity method, which will have it to be identity which falls on here, and as well to be identity which falls on here. Okay, so the identity have to come within the two different qubit gates of over here. Okay. Next to two qubits into be a like how do we checks into the work of WC naught, the C naught which shall have it to be a G naught and V naught. So this G naught and V naught which shall requires into the turn of that, the requires turn which shall have it to be a methodology of the work, like C and then alpha 0 and beta 0, and I mean 0s and 1 and 1 and 0 and 1 combination have been worked with you. Okay, so this shall be works within to be a different manner of the work, and this different manner can be succeed with the different technology based of it. Okay, this different technology have been works within the different streams of the work. This different streams can be comes into be a probabilistic turn only. This probabilistic turn comes the part of as per the row and as per the column, which will continuously close of the work. Okay, here it will be mentioned the matrix turn, which shall be have the value over here. It shall be having the computing the value. This will computing, and this will be equivalent to the value of a like to be RHS. Okay, there is a R and to be there is a L, which is to be equal over here. Okay, there's a condition which shall falls over here. So I'm just taking the value of WC naught, that accordingly which shall works individualistic two qubit gates have been worked over here. Okay, one it does be work, we shall get of a equivalent prospectors, equal perspective have been worked. Okay, next here there is a final comments of a C and C naught gate. Okay, the C naught gate which shall preserves the control qubit. Actually, it shall be works with the first and second component with the input vector, which shall have replicatedly with the output vector, and it shall have to be flips the target qubit. Third and fourth component have been worked the input vector before the fourth and respectively. The third component which shall comes into output vector. Okay, the C naught gate is reversible, but the things which is being happen into control qubit, which is to be replicated at the output and knowing the reconstruct the target of that. The reconstructing the target is to be input qubit. That input qubit which shall be happens is to be a final comments of the work. So that final comments of the work which shall represent into be a targeting the input qubit. Input qubit perfect input and output have been supposed to get back. Example, there is an example of one qubit gate which are applied with the two qubit thing. So here we are not doing nothing over here. We're not doing nothing over. And here there is a universal thing. Universal turn we are doing it using of a two qubit. Okay, either a 0, 0 or 0, 1. Okay, this two qubit we are taking over that. Okay, next thing is, so map basis state says, so with this map basis state says like into be a 0 and 0, 0, 1, which is representing into be a 4 cross 4 matrix. I meant into be a 4 rows and 4 columns which shall be appear. So this will be a one qubit applied with a two qubit system. Okay, this is what which is happening over here of a according the map basis of the states over here. Okay. Here the next is the question, what happens if U is applied for the first qubit? If the U is applied for the first qubit, what could be happen? Let's see. Control the U gates. We're supposed to be used and to be control the U gates, which shall works with that. So we shall see the mapping of the value of U gates. So U gates mapping with the 4 cross 4 matrix. So with this 4 cross 4 matrix, which shall be works with the 1, 0, 0. So 1, 0, 0, 0, 0, 1 and 0, 1. So identity matrix which shall be works into be the turn of values and 2 cross 2 and 4 cross 4. So accordingly it shall works with that. So this is to be called as map based systems and map states of the work. Okay. So actually, what is the question will be used? Where, like, if we suppose to use the universal term, how do we get back the value of the universal, right? So this get backing the value of the term. So that is the answer of the question. Okay. Here is the next. The control system have been used over here. So large with an x value, the x value which will be comments with it to be a alpha and beta. Okay, so this could be a alpha and beta, and there is a turn of the value which will have it to be a continuous progression which will use for the operations. Let's see one by one. So there is a control qubit. The control qubit may be into be a maybe a change or some input states have been used over here. That input states which shall be used to be a 0 plus 1 and which is equal to 0 minus 1. I mean, qubit maybe change the some input states, which the input states have been used within to be as per the state gate value. As per the gate value, if it takes the gate value have been continued with the state here. Okay, let's see if the gate value continued with the state over here, h plus h, and to the gate value have been combined with the NOT gate. Okay. There is an operation which shall be progressing with the NOT gate, and here the multiplication problem where shall be used with its here. Okay, so there is a multiplication problem. So there is name called like grade school algorithm. For example, if it takes input to be a 2 n bit numbers, if it takes that will be gives the example of it to be a 1,101 and 111. Okay, so we shall have those two things. Okay, so those two things we may have this into be a output to their different product of the cluster. For example, if I take this of 101 and it just takes in the value of 111. So if it takes the producting, I mean multiplication, if you're doing it, we shall get the value of this. So grade a school algorithm takes into be a in square steps. Let's see. So we shall see that basically best currently known classic algorithm cost is to be n log of the method. Okay, there is a best n log of the method is to be call it as quantum method. That quantum method can be used with the same one. Okay, used with the same one. That using the same one into be a same methodology turns of the work. Next, factoring the problem. So where we are factoring the problem, we shall take part of the input into be n bit of number. The n bit of number brings out to be a 101 and 1,1. As I already told you, if I gives you this answer, so which two number multiply to get this answer? Which two number if it takes the multiply to get the answer? If it takes the name for it to be a factorization, right? So that factorization can becomes within to be a factoring the method to be producting the level of the work. Trial division. There's a trial division cost it to be 2 power n by 2. So there is a 2 power n by 2 already, which was mentioned at 2 square, right? 2 square that will be taken to be 2 power n by 2. That is a trial divisioning method. So that trial divisioning method, which shall takes into be a best part of it to be currently classical algorithm, which will takes cost of it to be a 2n by 1 by 2 log of 2n by 2 by 2 n. Okay, this 2 by 3 n log value of it. Like hardness of factoring, like to be multiplying the value that shall comes into be a turn. Okay, so the okay, but the basis of security manner which will have into be a crypto system. That crypto system call it as so that crypto system will call it as into be a like RSA method. That RSA method can be works with the classical algorithmic turn. So that classical algorithmic cost turn which will comes with into be a hardness of factoring. The Shaw's quantum algorithm. So there is a Shaw quantum algorithm which shall be has into be a log of n. Okay, there is a log of n. Like to be if it takes into reversing a technique shall takes part of a time. We felt that to be very complex in the computing we were doing, like we felt it. Okay, as we are doing directly, we won't feel as to be doing the complex value of the work. The complex value of the work that shall comes with it to be a commit with two direction method. The factoring problem which shall has it to be two directly method. that implementing the break with the RSA with the crypto system. So Grover's searching algorithm. So Grover's searching algorithm, which will have into search into the database with the n names, and names are to be randomly entered. The randomly entered into be classically average of n by 2 search is required. Okay, that that O of n operation is required. The quantum computation requires it to be a square root of n. Okay, square root of n, I meant to be square root of n number of functions. So that is already, we have got some idea about previous resource person who have been explained well of Grover's model, right? Grover's, so like how do we quantum algorithm works? How does the algorithm works into here? Let's see. We just give a polynomial. We just give a polynomial time of classical algorithm. There is a function of values. There is function of 0, 1, which shall takes part of it n number of values, which is straightforwarding to construct a quantum algorithm. Okay, that will create the state which 1 by root 2 power n summation of f of x. I meant to be a function of x. This is not performing exponentially many computation which shall be happens into polynomial cost. Okay, the most straightforward way to extracting the information from state yielding of the work. It just to be x comma f of x for a random and the 0, 1 power n. So, but we can make some interesting trade of that. So we can make some interesting trade instead of learning about any x or function of x. That will be learning something global property of that. Global property is to be centralized property of function method. Okay, that centralized property function method can be done with this one. There is a dual touch problem. So let's see on the problem. There is a using of 4 possibilities. If it takes a function of 0, 1 and 0, 1. If it takes this, we are doing in the possibilities of the 4 possibilities. Just look on here. One is the one possibility which shall have into be a 0, 1 and which shall takes into 0, 1 and 1, 0. If it takes the value of false, the values, the output have been comes into false. If it takes the input true, the outputs to be a false. And there is a next combination 0, 1. If it's a true, again the function is true. And second state category, if it's a false, also to be a function is false. And it's true if it's again the answer to be a true state of the work. And there is a function 4 of x to be a 0, 1 and 1 and 0. There is a true and the category value is false to be taken here. So there is the problem which shall be mentioned using of a function of the category. So we shall determine the goal of the value 0, 1. So that goal of the value can be determining the classical method to using of the 2 queries which shall needs requires of the work. What about the quantum method have been worked over here? Like to be reversible black box to be function. As I told you already, which shall be used for the same computation, direct computation method can be accessed. If it's to be a reversible computation method, cannot be accessed with the work. Okay, so that is called it A and B and UF. If we takes that UF will be reversible turn of the work. So there is alternative notation. That alternative notation which shall has it to be a classical algorithm. The classical algorithm to be still requires of a 2 queries. That 2 queries which shall have it to be a f of 0, function of 0 and function of 1. Okay, the function of 0 and function of 1 which shall have it to be 2 different queries which shall be mentioned to be a classical algorithm. That classical algorithm which shall gives it to be a different stream or different strategies over here using of it to be a reversible black box one function. There is if takes to be a 2 queries, but plus 1 auxiliary operation is being needed. 1 auxiliary operation is being needed. Like how does we supposed to use it? Here, there is a 0 and the 0 which will comes into be h of f and to be again to be h f of 0 and f of 1 which will have into be h is equivalent to 1 by root 2. That 1 by root 2 which will come here 1 1 and 1 comma minus 1. So this quantum algorithm often to be a works with 1 query plus 4 auxiliaries. Just look on here 1 query. One query and the different quantum of the algorithm. Okay. And the quantum algorithm of 1, which will have into be a 2H and which will takes into H3H of them. So this will be function of category and then shall be recreates the state 0, 1, which shall be happens to be a vectoring method of a not category that method of not category not within a value of -1 and to be a positive value. Okay, we do have into two different algorithmic state over here. This will be caused for the function turns to induce the phase shift. Okay, function turn to induce the phase shift, which will comes with them to be a negative as well into be a positive. The negative state, which will takes into be part of f of x, that could be takes into brings into be a x category. This x category, which will have to come with a 0 to 1 and 0 to 1. This is to be happen and to be phase wise shift. So phase shift was it been working with it to be different manner and the different streams of the work. It's name called the quantum algorithm and cause f to be in queried with superpositioning value. Okay, that superpositioning value function value is 1, 2, 3 or 4, and this will be works with it to be a function of value and to be a -1, 0 and -1, 1. So then this value f1 of x, f2 of x and f3 of x. So this is all takes part into function 1, 2, 3, 4. So this will be comes into be a direct value of to be 0 to 1 and to be communicate with the value, the position based value. Once the value has been positionized, the causes may be happen. The causes may be happen that could be comes back again to the queried question. So here are the question to be a positive one and to be the next one level is to be a negative state. So positive and negative state shall be happen. And distinguishes the between of the positive and negative. If we are distinguishing the states of the positive and negative, shall see here like to be a positive value 0 plus 1 to be 0, 0 minus 1 to be either plus or minus, factorizing the term either a plus or minus to be a 1. Okay, shall be works to that third quantum algorithm. Summary. So like to be summarizing the like quantumic based of algorithm, which makes into one query. That one query whereas to be two are needed classically often. This shall be produces the superpositioning of an input of function 0 plus 1, which shall extract the phases differences from the -1 to be the -1 of the value. Since because we have taken the value of zeros and ones only, that zeros and ones will be construct the line vector so to be f queries induce the phases. That phases which shall happens into be f of x to be gather over here. So that gather 1 out of 4. 1 out of 4 search, like 1 out of 4 searches, like f function 0 to be a property that exactly 1 have been used. That 1 exactly have been used to be a function of x is equivalent to 1. Okay, that function of x is equivalent to 1, which shall takes part the values to be here. So let's see. There are 4 possibilities over here. The 4 possibilities over the turn of f of 0, 0, 0, 1, 1, 0, 1, 1. So those 4 possibilities have been worked with here. Just see that to be a false, be true. Again to be a false and true combination of the value, and to be a possibilities will get 0 again. 1, 0 also 0. Then there is a true, two true category also can be gets into false. Okay, as well 0, 0. And as well next one is 0, 1. There is a state where there is a 1 presenting into be here. There is a 1 presenting. Other thing category into be a 0. Okay, next 1, 0. 1, 0 where there is a 1, 0 is representing the 1. And next 1, 1 where there is a 1, 1 is representing there is a 1. So 1, 1, 1, 0 and 0, 1 and the square of the third 1 out of 4 searches. Okay. So there is a goal. So it's the goal to be x of the x summation of the like to be 0, 1 square for which f of x is equal to 1. So what is the minimum number of queries can call it as classically and quantumically. So classically quantum algorithm of 1 which shall take that there is a black box of a 1 to 4 searches which will be happens, and that x2 will be takes part into the function of x2 again. So y is to be function of x1 and x2. There is starting by creating a phases and superposition of inputs to the function. There is inputs to the function superpositioning the value and h. Okay, 0, 0, 1. There is a 0, 0, 1, which will have to be function f. Input state to query. So input state to query, which shall be has with the output state query of the. So input state, there is a call it, there is to be mentioned it over here, like to be a, so there's an input state. So we are just bringing out into the output state to be collaborating or to be adding up with the, to finding up searches with the one, start from a 1 to 4 searches we are doing and to getting the value of quantum algorithm. Next, there is a quantum algorithm part category of 2. So how do we get the part of a first 2 qubits? Okay, in the 4 cases, we do get a 4 cases. Case number 1, if there is a 0, 0, and we shall get of B method of the first case. Second case 0, 1, we shall get the value over here. And the third case 0, and there is a get the value over here. And the fourth case, and there is a 1, 1. So 1, 1 we shall have to be here. So what is the noteworth of a property 2? These statements have to be. So all the statements have been used for an orthogonal statement. The orthogonal statement have been used over here. So orthogonal statements have been used here. So to be apply a U that maps have been worked with the VRA method. The VRA method have been worked with the to be a 0, 0, 0, 1, 1, 0, and 1, 1, which will have to be respectively to the quantum state of an algorithm. So just look on here. There is a looks. There is a looks which shall be mentioned over here. HH. There is a function which shall have to be a universal algorithm, universal gates. So we shall have a combination pattern of the universal gate and to be a quantum algorithmic pattern of 2. Okay. So what makes the quantum algorithm potentially faster with any of a classical? So that is to be first one is quantum parallelism. So it shall have to be using with superpositioning of a quantum state, which shall computer is executing. So how does it to be executing? It does need of all possible inputs at once. Okay, that dimension of quantum Hilbert space, the size of a state space of the quantum system is exponentially larger than. Actually, it is exponentially larger. And how does it to be exponentially larger? It's corresponding in the value of classical system. Okay, that entanglement capability is different subsystems can be worked with the qubits. Okay, that qubits will be works with a quantum computer. It becomes into be entangled, exhibiting the non-classical correlations. The non-classical correlations have been worked with into be a different terms of the work. There is it requires a more quantum algorithms in order to solve the problems or more efficiently understand the power of quantum computation. Okay, so where we are understanding the power of quantum computation, that will make valid and also to be realistic assumptions to be confirmed with the insecurity process. Okay, that problems will call it as into the quantum algorithm researches, which will require close collaboration between the physicist and to be computer scientist. Okay, highly initiative of quantum physics. Actually, even like to be even to compared with all of the algorithms or classical or anything, which may have to be a research is to be very difficult to be turned with the work. Okay. Next, there is a summary. What is summary of to be like how I'm summarizing the quantum algorithms may be useful, possible to solve a problem to be quantum system method as much faster of them using of those fewer steps. Okay, and we are factorizing, we are searching the examples of problems where quantum is to be algorithms, where quantum algorithms are known as faster than classical. Okay, which this implications cryptography, which will have it to be information security. Okay. The study of quantum algorithm and to be quantum computation is more important in order to make assumption of to be a adversaries algorithmic and computational capabilities. Okay, which are leading to understanding the computational power and as well into be a classical system. We may have those two categories of the work to be summarized into the quantum algorithm. I just want to be conclude with this one using of this Shaw's and quantum algorithm. In 2001, they have started to be using for the 7-qubit machine was to be built with a program to run with the Shaw's algorithm to successfully factor of 50. And like what algorithm will be discovered next, and can quantum computers Okay. Does the quantum computer solve any complete problems to be polynomial type? So this was to be a next thing of that, to be a what to say, that next thing of a different turn of the work. That different turns to be brings in the so this different turns to be works into be a different manners of the work that be solved with a complete problems into be a polynomial state of the work. So actually, we were using into be different streams of the work. That different streams can be prolonged with or provided with into be a different manners. Okay, and what do we say? Like actually, to reducing the work of the work, to reducing it, and to along with that, detecting the turn to be come up with the 0 and 1 category, which is integratedly completing the category of the work. Okay. Yes. Okay. Is there any I'm just trying to completing things. So is there any doubts? You just please ask me. Let me clarify it. Hope one of the secretary has been
Participants, if
dropped
you
a
have any
message.
doubts,
Yes, ma'am.
Yeah, am I
Dear
audible?
participants, if you have any doubt, just raise your hands. We will
Yeah. Hello.
Yes, sir. Yes, sir.
Yes, sir. Please proceed.
Yeah. So the speaker actually compared between this classical probability and quantum probability in a slide, and I think there is a subtlety in that discussion, especially when she wrote that superposition state. I mean, the classical probability px was just replaced by alpha x, the probability for a particular state, either it's a ket 0 or ket 1. So if possible, can you just differentiate between this classical probability and the quantum probability, or in more precisely, what she can talk about a quantum state and a classical state with respect to the probabilities?
Okay.
How will you?
Quantum state. Sorry, sir.
कितना लंबा खेला था, कितना अच्छा खेला था तुमने कल, पता है? बहुत अच्छा खेला था.
Sir, can you just make louder, sir?
Yeah, and on a particular slide, actually, you try to compare this classical state with quantum state, right? Am I audible?
Yes, sir.
Yes,
sir. You are audible. You are
there was
audible
a
now.
subtlety. There was a subtlety in your explanation, because when you wrote the superposition state as the sum over the probabilities with a ket, basically, you said that you can replace this px, the classical px, with your alphas, right? So my question is basically this: can you just simply do like that? I mean, how this classical probability differs from a quantum probability, or what precisely you can talk about a classical state?
Actually, like you
And
are
a quantum
mentioning
state
about the
with
slide number 28, the classical and quantum system states to be work, and it's to be a probability the works to be distributing all the probability of the work 0 and 1, including the turn. Okay, which will get first turn is to be sum of all probabilities to take part of a distributing the value of 1, and other probabilities can take part of a random variables. First thing is we shall take all the probability has to be
I'm not getting
summation
my
of the value.
question.
Second probability.
That is conservation of probability that you are talking about. It should be preserved in both classical and quantum case. Okay, I have no problem with that. Absolutely no problem with that. But when you talk about classical probability and quantum probability, there is an issue. You cannot simply replace. That is conservation of probability that you are talking about. Be preserved in both classes. That is preserved. That is preserved in both classical and quantum case. Okay, that is not my issue. My issue is that when she talked about probability and quantum realm, there is a complete difference between how we deal with probabilities, especially when you write the probability that you are talking about and the classical probability, they are completely different. Yeah, of course, the conservation of probability need to be preserved in both cases. That I accept. But I think there was a subtlety, because my question is basically based on the last 3 sessions, what I have heard from others.
Thank you very much, ma'am, for delivering such an insightful and engaging session. So, dear participant, the session feedback available in the chat box. So, kindly take a moment to fill out the feedback.
அன்னைக்குதான் வாங்கியிருந்தோம். நம்ம எல்லாம் விளையாடிட்டு இருந்தோமா, இது ரெண்டும் உள்ள வந்து ஏதோ வேலை வச்சுட்டு இருந்துச்சு. வந்து பார்த்தா அந்த மேல 2 கண்ணு மாதிரி இருக்கு, கருப்பு கலர். அதை மட்டும் டெங்கின்னு பிச்சு வச்சு. நான் கிடையாது, நீங்க இல்ல, நீங்க நல்லவரு. நல்லவரு, நல்லவரு. அதனால இது
Dear participant, kindly fill the feedback link available in the chat box. So, valid up to 10 p.m. today. Dear participants, so today we are going to wind up the session. So tomorrow, so 6 to 7:30 p.m. So the resource person Silveraj CEO makes lab Bangalore. So the next session 6 will be start by 7:30 to 9 p.m. So Leti Wakumatori resource person HOD Dolby University Ethiopia. So once again I will repeat. So tomorrow the session will be start by 6 to 7:30 p.m. Resource person Mr. V Silveraj CEO makes lab Bangalore. So session day 3, session 6, 30 to 9 p.m. So the resource person, Mrs. Leti Wakumatori, so HOD Dolby Domo University, Ethiopia. Thank you. So dear participant, kindly fill the feedback link available in the chat box.